do we have in C programming?
Off the top of my head, I remember like the character and the int.
Characters, ints. Excellent. Any other types come into mind?
Double.
Double. Excellent. So we have char, int, double. So that's 3 so far. Any other ones that come into mind? All right, no worries. So a couple other ones. If we have our list of char, ints, floats, we also have doubles. We have long and short, which we don't really use a lot. And we have a pseudo type, strings. So for strings, how do we create and use strings?
Using the. Wait, do we have a. Oh, yeah, it's just a type, not like a.
So string is the one variable type we use that isn't a type in itself, and it's just what in our programming? How do we use strings?
As characters.
We use strings as characters, and specifically characters in what form?
Character arrays.
Character arrays. So if you think about a string, you notice that a string just has a bunch of characters in it. So in C programming, to create and use strings, all we do is create an array of characters. Now, let's take a look at some arrays of characters and see what we have done with them in the past. So I'm opening up my string demo right here. So indeed, if we take a look at line 9, we do see that we have this character array called word, and we're able to set that character array to a string, which is amazing. So because strings are character arrays, it allows us to manipulate strings in various different ways. All right, so if I go back to the types, so continuing on with the types and the variables, how do we normally initialize a variable in C?
Initialize. Right. We do the type.
We use the type, and what else do we need to do when initializing a variable?
We have the type, we have the name of the variable,
All right.
and if applicable, then we have parameters and semicolon.
Yeah, excellent. So we initialize using a very standard format, and that format is the data type followed by our variable name. And that's a very basic variable initialization right here. We just give it the type and we give it a name. And optionally, we could also give it a value by using the equals assignment operator. So we could just have equals and then value. And that's pretty much how you would create a variable in most scenarios. So let's take a quick look at pointers. Now, what do you remember about pointers? What are they in programming?
They don't have a value, but they point to a value.
They don't have a value, they point to a value. Excellent, excellent. So here's a little short exercise. I would like you to go on tutorials point and just briefly look over their pointer section. And once you do, tell me if you found anything new that we could add to our list here. So type is the pointer's base type. That's saying when you create a pointer of a data type, then the value of the variable that your pointer points to is of the same type. So if you have an integer pointer, then the thing it points to is also an integer.
Okay.
Yeah, so it's just keeping your types aligned. Anything else that you've noticed from looking over the pointer section?
The asterisk used to declare a pointer is the same asterisk used for. Oh wait, no. The asterisk is used to designate a variable as well.
Excellent. So that's telling us that whenever we're creating a pointer, it's a little different from when we create a normal variable. See if this lag here. So we're going to follow the same format. We're just going to have our data type. But in this scenario, we have an asterisk here before our var name or our variable name. And that lets us know that we've created a pointer. Now, could we, like using a variable, do an assignment like this?
I want to say yes.
All right, so let's say that you can put a value into a pointer. That's not a bad assumption because as a variable, it does store a value. Now, this is different from other variables in the sense that what is the value that you store in a pointer?
It's not the value of what you point to, right?
You tell me. You have the page pulled up, don't you?
I do.
So I recommend going to the What Are Pointers section. Hello, welcome. Here for the Intro to C review. Excellent, excellent. So right now we are covering the fundamentals, essentially. We're doing a quick review of variables and such. So here's a little survey. I would just like you to complete that towards the end. Get it back to me when you have it finished. So my question right now is, what do pointers store?
Addresses.
They store addresses. So when we are using pointers, we have to keep in mind that the value inside of it is an address, and that address is what it is pointing to. So instead of saying our data type variable name is equal to a value, we say that is equal to an address. All right. Now that we know this knowledge, how do we use it? How do we get the address that we want to store in a pointer?
So use the ampersand.
Ampersand. Now this is the address operator, and it will take the variable or whatever you are looking for the address of, and it will give you the memory address. So normally when we use pointers, when we create them, we set them equal to some variable's address using the ampersand sign. Excellent. So I feel like we've covered pointers pretty decently here, but now that we know that it stores a address and how to store that address, what if we want the value stored by the pointer? How do we access the value of the variable your pointer points to?
Use the asterisk.
Asterisk. Now, the asterisk is used initially to create your variable, and it's also used to access your value. So the operation would be, for example, if var name up here was our pointer, then to access the value inside of it, we'd simply use asterisk followed by your pointer name, and that gives you the value. That gives you the value of the variable pointed to. All right, so let's show a quick demonstration of said. Let's see if I can find my. Excellent, excellent. So we're going to take a look at these pointers here. Disregard this fun function. We're not going to take a look at it yet. But as we've seen before, the variable initialization is variable type, variable name, and we can optionally set it to a value like we've done here. And likewise, with the pointer, we know it's a pointer because we initialized it with this asterisk here, and we've stored the address of x using the and sign here. So there are some questions here, and these questions are, what is the value of x? We can see that it's 0. Excellent. So what is the memory address of x? X is somewhere in memory, and we don't know where until we do what?
Just print the address. Is that the second line?
Yes, we need to print the address, but how do we know what the address is? How do we get it?
Using the ampersand.
The ampersand. Because when we first create a variable, we don't know where in memory it is until we use the ampersand operator that tells the compiler to go look for it. Now, what is the value stored in PTR right now?
Just the memory address.
Just the memory address. And like all other variables, pointers themselves have memory addresses. So let's take a look at this output here. So we see that the value of x is indeed 0. We see that the memory address of x is this value, which is also the value that is stored inside of our pointer. So our pointer contains the memory address of x. And the value of x can be accessed using the asterisk operation that we talked about earlier. So that's pointers. Pointers are able to store memory addresses, and we're able to access the value of the memory it's pointing to. So here's a little food for thought question. What's the benefit of using a pointer instead of just using a variable?
What was the question again?
Why use a pointer and not a variable itself?
You can modify the contents of the variable without directly referencing or accessing the variable.
Excellent. That's really the fundamental benefit of pointers is it lets you access values that you normally might not be able to access. Now this ties us into our next topic, which is scope. Now pointers let you sort of go out of your scope and do things you wouldn't normally be able to do. So for example, if we had a variable in main and we had a pointer to that variable, as long as we have access to the pointer, no matter where we are in our code, we also have access to that variable. And what I mean by that is, take a look at this fun function here at the bottom. It takes a pointer as an argument, and it takes a value. So from this simple function here, what do you guess is happening? What is the purpose of this function that uses a pointer?
It's setting the pointer equal to whatever you put in the value.
Yeah, so what this lets us do is as long as we have the pointer, we can set the value to the variable it points to no matter where we are in our code. So pointer points to x, but because it is a pointer, we can change x's value from inside of our function, which would normally not have access to that variable. All right, so now that we know how pointers kind of help us with scope, what is scope? What does scope do for us? I want to hear some hear some knowledge. What does scope do for us?
It, depending on how you use it, can restrict
All right.
your access to a variable.
Excellent. And that's also an essential piece to coding, is that you want to know what has access to what, and scope is how we're able to define that. Now, it's not always easy to know what scope your variable is in. Are there any ways to figure out the scope of your variable?
Like, besides just reading the code.
Okay, so reading the code, how do you read the code and know the scope of a variable? What do you look for when deciding that?
Where it's declared.
Where it's declared. That is a great hint to where the scope of the variable is. So if we take a look at this x and this pointer, what is the scope of these two variables?
Local or function scope is what it's called.
Function scope, so they're both inside of main. And now a really easy trick to deciding the scope of a variable is look at the brackets that enclose the variable. Because the brackets that enclose these two variables are from main, we know that the scope is in main. Now, if I had a variable outside of those brackets, let's say I just had it out here outside of my main, what is the scope of this variable y? Why is it global?
It's outside of any function.
It's outside of any function. So as far as our program is concerned, y is able to be accessed from anywhere. Now, where your variable is located is one part of the scope of your variable. Are you aware of the other ways we can define the scope of our variable?
Oh yeah, was there something you could type before the
Yeah, so there are various keywords we can use to specify more clearly how we can deal with our variables. Now, I haven't mentioned this to you yet, but on the UCF Study Union WordPress.com website, on my page, I have a couple links that you might find useful throughout this session. One of them is this here, tutorialspoint.com/cprogramming. So let's take a look at some of these scope rules that we see from this website. So, as you've said, variables that are declared outside of all functions are called global variables, and variables that are inside of a function or a block are called local variables. Now, a block is any code within two sets of braces. That is what is considered a block. All right? Pretty straightforward. All right, so let's take a look at take a look at these variables here. It's not here. But as we were saying earlier, with the other ways of specifying the scope of our variables, there are keywords. Are there any keywords that pop into your mind? I'll give you a hint. Here's one keyword. It is static. Now, when you declare a variable as static, what are you saying to your compiler? You can change it, you can modify it. Okay, I can see where you're going with that. In what ways does it help you do that with the static declaration?
I mean, I just remember from Java when you declare a variable static, you can't. It's just basically it's a constant.
Okay, I see. So I just want to clear up a little confusion because I know that Java is a pretty straightforward language. I've used it for a number of years, so I recall that as well. But it's a little different in C. In C, when you say static, static normally means, to stay still, to not to move. So when we make a variable static in C, we're saying whenever we modify the value, we want that value to stay with that variable. So if we had, for example, a variable in our main that we've declared static, and we've modified it somewhere else outside of our scope, by keeping it static, that value stays with the variable even when your program is done running. So it helps when you have multiple files working together. You can have static variables that will keep their value so that you can use it later. That is the benefit of static variables, yes.
So you can modify it, it just resets itself?
So that's the thing, it doesn't reset itself. It keeps the value you give it until the entire program is terminated. So it's useful for the cases where you want your value to stay with your program. Let's say you did some calculations, you found the speed of light in one program. Because you kept that variable static, that value you have can be used in another program that will call your variable. So the value will stay there. It won't get reset when your code finishes running. All right, so if you give me just a moment, I'm going to rummage through some things. It doesn't seem that I have them. Any other variable keywords that you guys can think of, or as an exercise could find that we can use? So I'll give you guys just a couple minutes, see if you can find the other.
Is define? That's for macros, right?
Define is used for macros. So since we're on the topic of define, what do we use it for?
So like constants. So you can use
We use it set for constants. Like whenever we need like a global constant, like for example, we can define pi and always have pi equal to a certain value that we can use later. Or very commonly, when using arrays, you can macro a max array size, and you can use that to define your array. So changing the size of your array is as easy as just changing the value of your macro. It's very, very useful in a lot of scenarios. So I'm going to add static here. Now static means, for simplicity's sake, to keep variable's value. All right.
Auto sounds familiar. Is that for this?
Auto is. So what does auto do when we create a variable using auto? Hey, don't worry. This is why you both have your laptops. And the wonderful world of the internet is your best friend as a programmer. Hello, welcome, welcome. Here for the Intro to C review. All right. So
I've never seen auto use.
all right. So I've pulled it up here on the board. So the thing that is of interest to us is what's known as storage classes. Now, auto is one of those. So whenever we use auto, it's sort of like how we normally declare a variable. We would have our data type, we would have our variable name, whatever value we want to store in it. Auto is sort of a default storage class. All the variables we create that we haven't defined with other storage classes are auto. It's auto by default. You can explicitly write out auto, or you could not. That's the reason you don't see auto a lot is because it's already built in. And the only reason you would write it out is to be more explicit about it. So auto is optional. All the variables you create initially are auto until you change them. All right, so we have auto, which is the default of your variables. Now there's also register, static like we mentioned earlier, and extern. So have you two pulled up this page yet? Yeah? All right, so tell me a little bit about register.
This I do not remember learning in class, that it's used to define what the variables that should be stored in a register instead of RAM.
Excellent. So registers are these tiny little packets of memory on your CPU that's used to handle a number of operations, namely really quick arithmetic. So we all know that RAM is blindingly fast, really fast, but registers are a million times faster than RAM. The trade-off is that they're very small. So they're normally only used to deal with very small bits of data. When you create a variable using register, your compiler is looking at your registers, and if there's a free register open, it will store your variable there. Now the benefit to that is that whenever you have to do something with that variable, it's really quick. When you have to do an extensive math equation, for example, if you have all your variables stored in registers, then the operation is really quick. And if you have a lot of data, the quicker you can do it, the less time you're going to spend on it. So registers are useful for storing small bits of data that you need to have quick access to. More often than not, you don't get to store a variable in register because your computer is using them. More often than not, your computer is already using all of its registers.
So that's like valuable real estate.
Oh, super valuable real estate. It's like Malibu, beachfront, you know, the works. The register is really nice. It's hard to get, which is the only issue with it. So we looked at auto, we looked at register, we looked at static. Can you tell me a little bit about extern?
Used to give a reference of a global variable that is visible in all the program files.
All right, so we've come full circle. Now, extern is how you would explicitly define a variable as local, or global, I should say. Before, we saw that if we placed it outside of any blocks or functions, it was global. Likewise, inside of a function, using the extern keyword, you can say, hey, this variable can be accessed anywhere. It's external. Even though it's inside of a function, with the extern keyword, it gives it global access. It adds global access to your variable. All right, so any questions so far on what we've talked about with variables? Pretty good. All right, excellent, excellent. So to transition, let's take a look at program flow. Actually, I will give you guys a choice. Since we've completed variables, we can pretty much tackle anything left on this list. So we have program flow, raise functions, structs, files, data structures, extras. So what would you guys like to transition to next?
I'll let you finish.
Do you feel good about recursion?
My test is going to cover recursion. So, but if you said you want to do recursion, we can.
Awesome.
It's going to be useful eventually.
Yeah, excellent, excellent. That's what I like to hear. Recursion is the plague. But it's once you know how it works, you can easily avoid all the problems that come with it. So what is recursion? What pops into your mind when you think about recursion? Yeah, so recursion is a function that calls itself. Now, here's some, let me draw this out for you guys. Over there should be good. Now, whenever you call a function, your function call gets placed on the stack. So let's say you had a recursive function called fun. Now, every time you called fun, it gets placed on the stack X amount of times until your program is finished. Now, because recursion is a function that calls itself, you might run the risk of stack overflow. Now, stack overflow is an error that happens when you have too many function calls in your stack. So how do we avoid stack overflow when using recursion? Having a simple base case. Because the whole reason we use recursion is because we're trying to solve a problem. And if our problem goes on forever, it's not really useful. So we need to know when we've solved our problem. So with recursion, we need what's known as a base case, a case that lets us know we don't have to call the function again. All right. So you might be familiar with a couple of recursion algorithms. Fibonacci can be written recursively, as well as factorials are also recursive functions. And there are a number of other ones. Would you like to see any of these written out recursively? Yeah, all right. So I will very quickly write out the, let's see, factorial recursion. So how do you know when you can use recursion to solve a problem?
That's a good question.
And here's the trick. So when you define a function such as factorial, you know that 5 is 5 times 4 times 3 times 2 times 1. That's how we calculate factorial. Now the trick is to notice that this bit here is equivalent to 4 factorial. So to solve 5 factorial, we need to take 5 and multiply it by 4 factorial. To get 4 factorial, we could take 4 and multiply by 3 factorial. So every time we're doing the operation, the whole can be solved by solving a part. And that's the essence of recursion, is you take a big problem, and by breaking it up into parts, you can find the ultimate solution. So let's take a look at what that looks like. So I'm going to have a int factorial. And now my parameter will simply be the variable factor that we're going to be solving for. So if I wanted to find 5 factorial, I would simply pass 5 into this function here. So we have our function prototype factorial. Now let's write it out. Factorial int factor. All right. So what is our base case for factorials? When do we stop looking for factors? When factor equals 1. Because the factorial of 1 is 1. It's not very useful to figure that out. So if our factor is equal to 1, then let's return 1, because that is the value. Or you could return factor. So the result is, once a factor becomes 1, we return it. Now we have to do our recursive bit. So if our factor was not 1, then we return, what do we return? So remember that as we go down the recursion, 5 factorial is the equivalent of 5 times 4 factorial. 4 factorial is the equivalent of 4 times 3 factorial. So it's essentially the factor that we passed in multiplied by the lesser factorial. So factor minus 1. Now, that's it. That's all you need to write factorial recursively, is you need your base case, and in this sense, our base case was once factor is 1, we return factor. Otherwise, we return factor times the recursive call of factor minus 1. So if we called 5, we would be returning 5 times 4 factorial. So let's just see whether or not we get the correct value here. So let's say factorial of 5 is %d, which is the integer specifier, and let's just call our function factorial. Let's pass it in 5. Hopefully everything just works. So, and there you have it. The factorial of 5 is 120. It's pretty nice to be able to see recursion in a simple function like this, because that's all recursion really is. It's your base case and it's your recursive call. The trouble of recursion comes when you have to figure out what that is. It's not always easy to see what your base case is or what your recursive call should be, which is why writing out your problem might help you see that. So there are 2 things keeping in mind when using recursion, and that's simply know your base case and also make your recursive call. All right, so this is factorial. Now you can modify this to do all sorts of different things. You could actually make multiplication recursive if you wanted to. But I'll leave it up to you to decide how you might go about that. But a lot of things we calculate can be calculated recursively. Recursion is kind of like an iteration. The only difference is that recursion involves function calls, while iteration normally involves a loop. We can get around that by using recursion. So since we're in the function section of our review here, let's talk about function initialization and definitions. So before you can use a function, what do you have to do? You have to make it. It's pretty straightforward. Before you can use something, it has to exist. Before you can use a function, you have to create it. Now, what is it called when we first create our function? It's called a function prototype. Without this function prototype, the compiler has no idea what your function is, where it is, or how to access it. Creating the function prototype lets your compiler do its thing and use your function properly. Now, what is the format of a function prototype?
We calculated SVM. The type is the first one, right? That's what's called like the ints. That's called like the type.
What kind of type is that? It is a type, but in terms of a function, what is that telling us?
Return type.
Return type. So it usually involves a return type followed by
Variable
followed by a function name, and then followed by a list of parameters, followed by a semicolon. Now that's your basic function prototype. Return type, function name, list of parameters. What are the return types that we have available to us?
Void, integer, character.
Void, integer, characters. Essentially, all of the data types are return types as well, with the addition of void. Now, when we use a void function, what does that tell us? It's not returning anything. Normally, a void function is used to do something, whereas a function with a prototype, it does something, but it gives you something back, which is useful. For example, my factorial function had an integer return type. So we knew that ultimately we'd be getting an integer value back from our function. Now, the function definition is completely dependent on what it is you want your function to do. But there are some things to keep in mind when defining your function, is that if you do have a return type, then the compiler is expecting you to return something. So if you have a return type and you're not returning anything, that will give you an error. Likewise, if you have a void function and you try to return something, it would also give you an error. So the takeaway, I'd say, is keep your definitions in line with your initializations. Namely, if you wrote your prototype one way, then the compiler is going to expect your definition to also be written that way. So if you have, for example, 3 parameters in your prototype, then your definition also has to have 3 parameters. Keeping it toe-to-toe will help you avoid a lot of errors when using functions. So, any questions on functions?
I'm still a bit fuzzy on parameters.
Okay, so what are parameters?
They're like, I'm not sure what drawing a distinction between a parameter and a local variable. Like to me, it's just a local variable.
And that's very true. For a function, the parameters can be seen as a local variable because they are local to that function. The thing to keep in mind whenever you hear arguments, parameters, those are what gets passed into the parentheses of your function. Now, an argument is the initial, actually, let's take a quick look over here at tutorials point. You have a really good explanation. Let's see if I can find it. Right here, we go to the functions. So the parameters are what you define in your prototype. But whenever someone says an argument, that's actually what you pass into your function. So parameters are what you define, arguments are what you pass in. But with the scope of your function, all of your parameters to your function are also local variables to your function. So if you've defined an int x, for example, in your parameter list, that x is local to your function. It's also a parameter of your function. It tends to be your parameters are also local variables in your functions. Does that help clear up anything?
It does a bit. It's mostly like the application. Like I see people use, in other people's code, I see like a parameter that's been defined, used to call the function. Like they said the parameter equals something. I think I've seen.
Let's see. So, for example, do we have? We seem to have a. All right. So let's just take a quick look. So if we look back at the factorial function here, we see that factor is a parameter. This 5, what we pass in is the argument. So the value you pass in is the argument, whereas what you've defined is the parameter. And the parameter will be used as a local variable inside of your function.
Okay, yeah. I think that clarifies things.
Excellent. Sometimes you just need to, look at code, especially a simple example, because they really help with your understanding. Okay, so are we good with functions, or is there anything else we might need to cover? Excellent. There is a small thing, and that's you are able to create pointers to functions themselves. So you're able to call and use functions using pointers. So this is the same benefit as when we have variable pointers, and it's that we can call functions in places we normally might not be able to. So, for example, in a whole other file, you can call a function you've created. So if I had this factorial function and I have a whole other programming running, if I created a pointer to that function, I can use it in my other code and it will work because pointers lets us go beyond the scope of what we've created.
Wait, so you mean function type pointer, function name, and then that's what you mean, right? Not like a pointer variable that equals the function, right?
So I mean that it is like how you described it. You just define.
When you make the function definition, you include the little asterisk.
Oh, not in the definition. You actually create a variable.
Okay, that's.
You create a variable, and that variable stores your function. Because unbeknownst to us, is your function name itself is a memory address. So because pointers store memory addresses, they can also store functions, and you can simply just pass in your arguments to your pointer, and that will go into your function, and that value will be calculated and be stored in your pointer. It's really quite nice.
How would you do that? How would I pass? So let's say I have the factorial function as a stored in a pointer variable, and I want to pass the value of 5 to it.
I believe, if you give me one moment, I will quickly look up how it's done. Pointers to functions. Let's see if there's a tutorial pointing at that. So let's take a look. All right, so here, no, that's not it. Function called by pointer. That's C++. There we go. Void get second. And that's not it. Not passing pointers. Function pointer. So here is the example. You have really good insight. So you knew immediately. So here's the function fun, for example. So to create the function fun pointer, you would need to have the same return type, so it's void, and then you declare your function, or you declare your pointer how you normally do, using an asterisk. But then you set it equal to your function. Simply using the ampersand operation, you say, here my pointer is equal to our function, and passing a value into your function is as easy as calling your pointer with the argument you want to pass into it.
Okay.
So it's really nice. You can do a lot of cool things using function pointers. They're not very common for a lot of the things we do, simply because we can already do it simply by calling the functions we already have defined. It's useful for when you're working with more than one file and you need to have access to those variables in other files. Java makes it a whole lot easier to do this. With encapsulation, hierarchy, it's very easy to do that in Java. In C, we have to be a little bit more explicit.
What if I just put all my functions in a header file and included the header file in each?
You could. That's the same thing as inheritance in C is. If you have enough header files of everything you need, then it works. This is why we have standard lib standard IO, ctype.h, because they all contain useful functions that we don't want to have already defined in our code, because our code would be massive if we included all those functions. But a header is a way that we can get around that. Function pointers is also another way we can get around that. Calling functions we probably don't have access to. All right, so I feel like we have a pretty good grasp of functions. So from this list here, we have a couple items. We have program flow, you have arrays, structs, file IO, and data structures. So I'll once again give you guys the option of deciding what we will transition to.
What should I do next? I'm gonna say file IO.
File IO.
Versus random access.
All right, excellent, excellent. So I'm going to go to my REPL page again. I actually have a couple of file demonstrations that I've written previously. So let's take a look at the first one. All right. In addition to this, I would also recommend you open the files section on tutorials point so that it would be easier to follow along with what I'm saying. All right, so a file is what in C? What have you seen on the page about files?
In our case, it's just a .text file. That's what you're creating.
We don't really use .text files. Let me go back to tutorials. Why might we need file access when creating our programs?
The output, maybe in most cases, just the output to the file is going to be more useful.
Excellent.
Actual software engineering sense.
Yeah, most definitely. Any thoughts you want to throw into that mix? Why use files?
It might be slightly less useful, but if you try to import data from another file into your program to use.
Yeah, let's say you have data already made for you and you want to be able to quickly access it. Having file IO capabilities is really useful for that purpose. So how do we use files in C? Well, first things first, we have our file keyword. Now, all the files we use are pointers because files are stored in memory. In order to access them, we need to have a pointer to that place in memory. Now, there's a very special function for files, and that function is called fopen. Now, if we take a look at the definition here of fopen, fopen returns a pointer, and it takes as its parameters, takes a file name and the constant mode. Now, we have a couple modes available to us. R, W, A, R+, W+, A+. So what does R do for us when we open a file?
Opens the existing text file.
And W?
Writes to the open file.
So those are pretty much the only ones we tend to use, R and W, read and write. Now, you might want to create a file that you can do both on, read and write. In order to do that, we would use D pluses. So R plus lets us do both reading and writing. And W plus will also let us do both reading and writing. So if you want to do more, just put a plus in your mode when you're opening your file. So in the case of my input.txt file here, my mode is R, so all I'll be doing is reading. All right, so this actually is a bridge to common errors, but when you use fopen, there are cases where the file you want might not be where you told the compiler to look. In that case, your file pointer ends up being null, which isn't a bad thing. What is bad is when you try to do function calls and manipulate a null pointer, because you can't do something with nothing. So more often than not, before you actually use the file pointer you've created, it's always a good idea to check whether or not you're null. Because if you're null, then you can't do anything with your file anyways. But if you're not null, then you can access, manipulate, and use your file. And there are various functions for accessing and using your file. Any functions pop into your head about accessing and using files? What functions have we used so far? There is fopen, and that, as we saw earlier, helps us to find and create our file pointer for our file. What other functions have we used for file pointers?
Fclose, fputs,
fclose, fputc, and what was that last one?
fputs.
And fputs. All right, so what do these functions do? What does fclose do for us?
It closes the file, right?
Closes the file. Why is it useful to close the file?
Memory leaks.
Memory leaks, possible. Yeah. So you remember how when, for example, you have a flash drive plugged into your computer and it's always better to safely eject before you pull it out? It's the same thing with files. You want to close that file stream when you're done using it. Otherwise, it stays in memory and it might be tampered with. It might get corrupted. It might be accessed by a program that's not supposed to access it. So it's always good convention to close your file that you're no longer using. It avoids a lot of issues. Not to say that you couldn't get away with it, but it's safer to close it. Just like it's safer to safely eject before you just yank your flash drive out. So fclose is useful. Now, what can we imagine fputc does for us?
It only moves character values into the file.
Yeah, fputc, if I can do this correctly, fputc adds characters to our file.
When would that be useful? Compared to just like writing the file.
It's useful when you want to be more explicit. Like, for example, you could write out the entire string, hello world, using fputs, for example. But let's say you want to, one by one, add them in. You could have a rule that says, if my input value is O, make it I. Using fputc, you have more control over what you're doing. It's really about being explicit, which is why a lot of things we do are character by character basis instead of just the whole string. So fputs would just it puts whatever you tell it to put into your function. But let's take a look at fputs. So fputs writes a string. So you could tell fput to write out hello world, or you can one by one write out whatever it is you're passing in. And there are a couple of other ones. There is fprintf, and honestly, if I were going to use any of these functions to do whatever it is I'm doing to my file, I'll use fprintf simply because we're very familiar with printf. We know how to do formatting, we know how to use specifiers, so it's pretty straightforward to use fprintf. So I'd recommend, if you need to print to your file, fprintf is here. It's here to save the day for that. Now, we know how to put stuff into our file, but how do we take stuff out of our file?
fgets and fscanf.
Fgets and fscanf. Now, fgets is like the opposite of fputs. Fputs can write strings, fgets can pull out strings. And now we have fscanf, which gives you the versatility of scanf of being able to scan in any value you want, strings, integers, chars. Fscanf, because you have that format, you can specify what it is you're taking from the file. So fscanf is very useful for such things. All right, so that's files themselves on a basic level, but we haven't really touched upon what the whole difference between sequential and random access. So just what do you think that means when your file is sequential or random access?
I can't think of that much of a difference. Like I can't think.
Yeah, because the terminology is a little off-putting, because it makes you want to think that, for example, if you have a sequential file, then you have 1, 2, 3, it's in a list, versus a random access file, you might have a 1 here, 2 there, 3 there. So it's not to say that your file is organized in any way. It's really a term of what's in your file. So sequential files tend to be the files we're used to. TXT files with characters and whatever inside of them. But there are also binary files. So in binary files, there's only zeros and ones. And you're not really sure what those zeros and ones are. That's the kind of randomness of your file. Is if you just looked at a binary file, you don't really know what's in it. But we have various ways of, using binary files, and there are two main functions. That function is fread, which takes a pointer. It takes the number of items you're going to be passing in, and it also takes the number of elements. It also takes your file. So what that lets you do is it lets you write or read to your file using a set amount of data, and it will just add that into your file. It's very nice because more often than not, the data stored in a binary file is chunk data. By chunk data, I mean, for example, we use structs a lot when dealing with binary files because structs are little packets of information such as char and int, all defined in one struct. And the beauty of a binary file is all those values, for example, will simply just get written to your file as a chunk of data, like this chunk of binary here. And there will be various chunks. And with binary files, all you need to do is iterate through all those chunks of data. And you can do that using fread, fwrites. But those are a little bit more advanced, a little bit more nitpicky, and we tend to not use them in Intro to C or even CS1, mainly because most things we do can be accomplished simpler using just normal file IO. But if you're interested, these two functions are here. You can use them to do file IO in the same way you can use the other ones. Just know that the files you're dealing with are in binary, zeros and ones. So if you look at it yourself, you probably don't know what's going on, but you could write a program that knows what's going on. So that's how I think about sequential versus random access, is with a sequential file, you can look at it, you know what data's there. Random access file, you look at it, you're not sure what's there. That's file IO. I recommend just going over the two file demos that I have on this REPL here, file demo 1 and file demo 2, and they'll give you some insight on file IO. File IO is straightforward. There are just things to avoid, like using a null pointer. Make sure your file exists before you use it. So make sure you do this check here before you start manipulating your file, because you might end up creating errors you weren't aware of. So if you want a quick, random access files tend to be in binary, and they normally only use two functions, fread and fwrites, while sequential files are not binary, or they're not explicitly binary, and you have a whole assortment of functions to use with files. So sequential, normal files, random access, binary files, and that will definitely help you differentiate between the two. It's also that random access files only have two functions that you can use with them. So they're a bit more limited in that sense. So fputs adds strings to our file. All right. And
I do have questions about memory leaks.
yeah.
So I'm taking out Uno, and he said he might insert some memory leaks into the program problems, and we'd have to find them.
Oh,
And
excellent.
He never said, like, he's like.
There are a lot of different ways that memory could leak out of your program. One way is, so you remember how I said there's a stack? So your stack grows up. There's also another part of your code, of your program behind the scenes, and that's called the heap. Now, the heap grows down. So you have your heap growing down, and then you have your stack, actually, heap going down and stack going up. So there are cases where if your stack overflows, you can end up writing into your heap and changing variables that are in your heap. Likewise, if your heap gets too big, it could write into your stack and potentially delete function calls that your program needs.
What class is that? Is that logic and organization?
Oh, this information right here? This is, what class is this?
CS1.
This is a course called System Software. Yeah, I'm taking that this semester. It's a pain in the butt, but that's besides the point. But this is really useful to know because your function calls are what adds to the stack, and whenever you declare and use variables, that's what adds to the heap. So, are you too familiar with dynamic memory allocation? So, let's go to the dynamic memory allocation section here. All right, so that's at the bottom here. So dynamic memory allocation lets us explicitly define how much memory we want to use. So as an example, I'm just gonna write it right here. Let's say we have an int pointer, very familiar with how that works, stores a memory address. But we were able to use functions like malloc and define a size. So we have this integer pointer, and we're going to give it a certain amount of memory. Let's say we gave it 1,000 bytes. So our heap is going to grow down by the size of whatever we dynamically allocated. So the issues you might run into is you use too much heap memory, and you end up overriding your stack, or the reversal, you have too many function calls and you end up overriding your heap. Those are very common.
What would some like beginner mistakes of memory leaks be? Because I think he might insert them with stuff like fclose, like it won't be an fclose of the program.
Mhm.
That's easy to look out for. Then maybe stuff with malloc, because we did do a lot of memory allocation.
So remember how we were talking earlier about safely ejecting, closing your file? There's a similar operation for whenever you're doing dynamic memory, and that's the function called free. So free takes that memory and clears it up. So imagine that this like code segment was in a loop, and that loop ran X amount of times, and every time your heap is increasing. Eventually, your heap's going to be too big. A way to get around that is if you're not using this anymore, you call the free function, and that will lift up the heap, freeing up the memory so that it can be used by other things. Because your system has a limited amount of memory. You might not notice that because your code more often than not won't be using a lot of memory, but there are cases where you do just use up all memory. Your system locks up, code doesn't work. You just use too much memory. Back in the day when you only had like a megabyte, that was a very stressful thing to have happen, running out of memory. Nowadays we don't worry about it too much because we just have terabytes. You have terabytes on your hard drive. If you use a terabyte in your program, you know, more often than not you won't be doing that.
In later CS classes, does that become more important?
It does. It's very important, memory management. So at least I want to stress it right now, is to do things like file close, to do things like free, because at the end of the day, you're going to have to anyways, because your memory is valuable. For example, your phone only has a set amount of memory, so all the code written for your phone has to keep that in mind. It has to be agile. It has to free memory it's not using, load up memory it needs. And as the programmer, you have to keep that in mind. Keep in mind that you use memory when you write code, and you can run out of memory if you're not careful. But that aside, let's get back on track here. So what should we transition to? Let me go back to the list. What should we transition to?
So we're in data structures now.
Yes, but we haven't really done much in data structures.
I would like to see what I wrote seriously there.
Are you fine with us just continuing on with? Okay, so somebody let me know, but what is malloc and calloc, and what do they do for us?
Malloc allocates the memory based on the argument you pass to it, so you can pass like size of, and you can allocate memory based on like the data type. That's how we do it in our class.
Excellent. Yeah.
I don't know what calloc does.
So malloc does allocate memory. Have you pulled it up on tutorials point? It's always a good tool, honestly. Tutorials point. Easy reference. Like I use it all the time because if you just need to know how something works real quick, it's already online. You don't have to reinvent the wheel to use it. But as you said, malloc does allocate memory to us, and that memory is, why is it misspelled there? But malloc does allocate memory for us, and that memory is dependent on the argument we pass in. And to assist you in your whole memory leak issue, there is a whole section on tutorial point about memory management. I feel that would be very useful for you to look over if you want to be more agile with looking at memory leaks. So we know that malloc allocates memory. So does calloc, but there must be a difference between the two. Otherwise, there'd only be one function. So what I want is, what is the difference between calloc and malloc?
It returns a pointer to the memory that you want to allocate.
Yes, so malloc and calloc are functions that return pointers. So that is something to keep in mind, is that they do return pointers, which is why we normally use a pointer when we want to define that space. But why are calloc and malloc different? If you look at the prototypes for both, they're slightly different. One takes simply one argument, while the other takes 2 arguments. So I'm going to pull that up so that we can take a look at it.
It said that calc says the allocated memory to 0.
Yes,
Malloc doesn't.
that's what I wanted you guys to find. It's that when you use malloc and calloc, you're accomplishing the same goal of reserving memory for your program. The only difference is that when you use calloc, you already know that all that memory you've allocated is set to default values. So remember how if we create a variable without initializing it, it might have a garbage value in it. And that value is simply whatever was there in memory before you created your variable. It's the same when using dynamic memory allocation. When you allocate a certain amount of memory for your program, you're not sure what's in that chunk of memory. Which is why using calloc is useful when you want to know that all that memory is a default value. It's not something that's going to mess your program up. So when you use malloc, more often than not, you're going to have to go in and set all those values to a default value. Using calloc makes that easy because the program does it automatically. You know it's all set to 0. No worries there. They're both very useful. You don't have to use calloc if you explicitly define what's in your memory chunk. Calloc just makes it easier, gives you peace of mind knowing that at least the values there aren't garbage values, won't mess your program up. So that's malloc and calloc. Now, what have we seen we've used malloc and calloc for? Not sure why the internet's not working.
Can you re-explain the explanation you just gave for calloc?
Okay, so when you create memory, I really wish I had like a little thingy thing. I'll just use this. I don't care. All right. All right. So let's say we decided we want this much space for whatever it is we're doing. And let's say this is like a size of 100. All this space is now available to our program. When we use malloc, we're pretty much playing a guessing game because we're not sure what's inside of this chunk of memory. It's just whatever was there is what we've allocated. When we use calloc, let's say this is the memory we've allocated using calloc. If we use calloc, you know that all of these values will either be 0 or null, default values.
So in like a practical use of that, like you wouldn't accidentally override memory, or you wouldn't. What would be like the practical use case? Because they seem to be doing more or less the same.
So think about it this way. Let's say you've allocated space and you want that space to be used in a calculation. For example, we're going to be calculating some physics and we need this amount of space to store our variables. And the issue comes in, let's say we immediately try to use this space and do some calculations. Because there are these garbage values, we don't get the results we want. We might get an error in our code. The reason you want to use calloc, or the reason you want to have default values, is because you want to have a base to start off from. So, for example, if you created x, right, and then you said x plus plus, we know what these 2 lines of code do. We created our variable and we've incremented our variable. What we don't know is what value is in this variable right now, so we don't know what we've incremented to. That's the same thing with malloc and calloc, is we've created the space, but when we try to use the space, we don't know what's there yet. So it's your job to know what's there before you use it.
So it's like the pointer equivalent, or like the memory allocation equivalent of saying int x equals 0.
Yeah, that's exactly what it is. It's saying int x equals 0. Now you know what your base is, you know? Either or you can use, because for both of these cases, you're still going to want to go in and, you know, put in values, different values. Calc is nice because you might want to have all zeros initially, and using that function makes it easy to do that. You don't have to create a loop, go through all your memory spaces and set a value. Calc makes it default by default. So the reason that this is of interest to you now is because of the data structures that we've seen previous. Let's see if I can pull. Is there any way to switch from the laptop to my laptop? Because for some reason, the internet's not working on this one. But the data structures that we have been introduced are linked lists, stacks, and queues. Now, you're familiar with stacks. You know that your stack grows over the course of your program. Things are added to the top of your stack, and then they're taken out of your stack. So we have the option of creating. Yeah, the internet wasn't loading a couple pages. So we have the option of creating that memory or a data structure that represents what our stack is doing. So stack is what's known as a last in, first out sort of thing. So 3, 2, 1. So if this is our stack, then 1 is the first thing that would pop out of our stack because it's the last thing we put in. A queue is a line. Think of it like you enter a line and the last person in that line will also be the last person to leave that line. The first person in the line is the first person to get out of the line. So a queue is like a line you wait into, while a stack is very much like a stack. You pop in at the top, you also pop out at the top. Two very similar data structures used in different ways.
What's implementation? Is like there's special syntax for implementing a queue and a stack, or is it just?
There is. So most important is to get used to the idea of how the stacks work. Is you put something in, and the last thing you put in is the first thing you put out. But with a queue, you're always starting first. The first thing that's in is the first thing that gets out. When you get into line and you're first, you're the first one they're going to help. If you get into a stack, if you're first one into the stack, you're going to be the last one to get out. So this one is last in, first out. This one is, let's see, last in, last out. Or you can think about it as first in, last out, or first in, first out. But they're different. They're different slightly.
You gotta go into settings for the computer about how you switch the media instead of it just being your screen share, it would be actually what it's on. How you do it on your computer though. So.
What am I doing? Oh, wait a second. Oh, that works. It's just extended. So I can just drag it over. Yeah. Wait, why don't you go? Go. All right. What? All right. Yeah. Forgive me, everyone. I use Linux because I hate Windows, and I'm also a programmer, so Linux just makes everything convenient.
What are we gonna need? Because I'm a CS major. I take CS1 in the fall.
Oh, excellent.
Are we gonna need Linux more and more often as we progress through the degree?
I want to say that you don't need to have like Linux on your computer to be a programmer. It's that a lot of the tools in Linux we use, like for example, we use REPL to do a lot of our compiling right now. I'm not sure if you do as well.
No, we just I hate code block.
So coding blocks, for example, coding blocks is an IDE. All of the tools to program are built into it. Linux, the operating system, all those tools are built into the operating system itself. So I could, for example, compile directly from my computer. I can write my file and compile directly from my computer. I don't need any third-party software or any VPNs to a Linux. I could just use it. But to continue with what we were talking about, these are data structures that we're going to be using. They're useful to us. And the last data structure that's useful to us is a linked list. Now, what is a linked list?
It's each node in the list points to the next item, points to the memory address of the next item.
Exactly. So let's say this was our node here. There's a value in this node, but there's also a memory address in this node. And that memory address points to the next node in our list. Let's call this N2. So a linked list is just all of these nodes in memory, but the node itself points to the next one. So it helps us propagate. So the reason it's important to understand the linked list is because this is how we often implement stacks and queues, is using a linked list. So if this was a stack, for example, this would be the last item, the first item, et cetera, et cetera. If this was a queue, this would be the first item, which points to the next item, et cetera, et cetera. So the implementation of your linked list depends on your, yeah, it would be a lot easier. It simply depends on how you write out your linked list. So it's essential to know that this is not continuous. I want to point out that even though your nodes point to the next node, this isn't all one block of memory. These nodes might be in separate places in your memory, but the benefit is that you always know the next node where it's at using our pointer to the next node. Now, we normally use a struct to represent our node. Now, let me just give you a quick demonstration of what that would look like. Is it possible that I don't think I need the monitor for what I'm about to do, so if I could just leave it off, that would be great.
Sure.
Yeah.
All right. I mean, no problem.
Yeah. Right. It's purple. That's weird. So here's a struct. So we have struct node. Now this node would store a value. Let's just give it int value. All right. But then it would have a pointer to the next node. So this struct here you see is a single node, while the next node pointer points to the next node. So yes, they're all the same structure. So when using dynamic memory allocation, what you're doing is you're saying, here's my struct, here's how much space I want to set my struct to. So that gets added to your heap. Whenever you do a dynamic memory allocation, that's something you add to the heap of your program. So very quickly, how you could create a linked list out of this is you can say that
struct pointer, let's say first node is equal to malloc, and then you define the size you want to set it to. That will create this first node. Now if you wanted to create the node it points to, you do a very similar line like this, but you would say that, for example, first node dot operator, because we're using a member inside of our struct. So first node dot next node, and then you can set that equal to another malloc line, for example. Now this would create what we see here with our first node pointing to our next node. Now you can repeat this process X amount of times until you get the entire linked list that you want to use. All right, so this is available online, so I'm not going to try and go too in depth into the linked list because it is a lot to talk about, but I want to cover the fundamentals. So you might be thinking to yourself, all right, I understand a linked list is a node that points to the next node, to the next node, to the next node. Let's say I want to add a value to this node, but I want all these values to be in order, keep in mind. So let's say this one was 1, 3, 5, 7. All of these values are in order. What if I wanted to add a 4? Logically, we want to put our 4 in between 3 and 5. So how could we go through our list and figure out where to put our node? What do you have to keep in your mind when deciding how to write the code for this?
The way I did it in my program is you have to have like several nodes, and each one kind of like. I gotta pull up how I did it. I forgot. It's like I used a while loop, and you kind of traverse the list with the while loop.
Yeah, so
Never did any insertion, but like the traversal node points to the address of the next one.
yeah.
And then temp one points to the address, and like you kind of increment to the addresses.
So take a look at this. So we know that every node points to the next one. So when you're deciding how to code for this, you simply have to think to yourself, well, while the node I'm currently at isn't, less than the value that I want to put in, then go to the next node. So if we start at the first node, 1 is less than the value we want to put in, so we have to go to the next node. Now we're currently pointing to this node. The trick is you're going to want a pointer that will represent the current node you're looking at. So this pointer, using a loop, will transition through your list until it finds the spot. Now, let's say you were at the 3 node and you decided that, well, 3 is less than the value we're putting in, so let's go to the next node. But now we're at 5. 5 is greater than the value we want to put in, so we're kind of stuck there. So what you would have to do is, in addition to knowing the current node you're looking at, you also want to know what the next node is as well. So you're going to want 2 pointers, one for the current node and one that sort of peeks ahead to see what the next node is. So with these 2 pointers in your linked list, now all you have to do is, when you're at 3 and you look ahead, you see that 5 is greater than the value you're going to put in. So you know that it goes in between these 2 pointers. So all you'd have to do now is keep in mind that 3 points to 5, but you want 3 to point to 4 instead. We can do that. We can change what this pointer is, and we can make it point to 4. But what's the trade-off of directly just saying 3 points to 4?
The address of the next one.
Exactly. We lose the address of the next one.
So you would have to have 4 point to the address of 2, right?
So we want 4 to point to what 3 used to point to. Yeah, so which is why we had that second pointer, so we don't forget what we pointed to initially. So now we just say that 4 points to 5 because we already have this pointer of 5. So by keeping these 2 pointers, then you're able to very easily keep track of where you are in your linked list. And another thing you want to know is that the end of your linked list is the node that points to null. If your node points to null, that's the last item in your list. So if you wanted to figure out a mechanism to go through your linked list, you know that your condition to stop is when you reach the node that points to nothing.
Yeah.
That's how you know when to stop. How you know where to insert and delete has to deal with what I showed you here. Keep 2 pointers because it will help you keep track of where you're putting something in or where you're putting something out. So if you wanted to delete this 3 node, you'd first need a pointer at the 1, and you'd also need a pointer at what 3 might have been pointing to, so that when you do the deletion, you know where to change your pointers to. So keeping logical track of your pointers is really essential to these data structures. So I want to continue then, unless there are more questions on data structures. But a lot of it, if you do want more information, is to look up a video on linked lists, and they will do a very in-depth look at the various functions and how to write them. My goal here is to get you to understand how you use them so that writing it becomes easier. Because it's easier to write the code for this structure once you know what you're doing, what to look for. It becomes a lot more straightforward. But data structures are an abstract concept that we make up, which is why we have all these various tools for dealing with them. And pointers, from now on, are your best friends. We're going to use them for a lot of things. For a lot of data structures, use pointers. Dynamic memory allocation, use pointers. So it's essential to have a solid understanding of what pointers are, because that's how you manipulate your linked list. You know that it has a pointer to the next one. You know pointers are memory addresses. So you kind of understand how it works. You go from one node to the next, sort of like a ring around the rosy sort of thing, where you just hold hands to the next node, and that's your pointer. So we've talked about pointers a lot. We talked about the dynamic allocation aspect of data structures. So I just want to briefly cover structs to tie this all together, because we need structs for a lot of different things. We use structs for binary files, and we will also use structs when dealing with these data structures. Now, if you take a look at this struct demo, you see I've defined 2 structs here in 2 different ways. So the first way is using typedef. Now when you typedef a struct, that lets you define your struct as a data type you can use in your program. So for this struct, I've typedefed it to person. So now person is a struct that has an int age and a char name. And we have this basic struct here called group that doesn't use struct. So whenever I want to call this group struct, you see that I have to include the word struct. Now I personally do not like to write struct every time I use a struct. So more often than not, I will typedef it and give it a reasonable name to make it easier to use. But there are a couple of things to keep in mind when using a struct. What might those be?
Any specific hints?
Since we know that a struct is a packet of data, how do we access the individual packets?
The dot operand or the pointer, I use the pointer thing.
Yeah, so there are a couple operations that come with structs. One is the dot operator, and the other is the pointer operator. Now, if you created a struct as a pointer and you wanted to access the members of your struct, you have to use the arrow, the dash, and the greater than symbol, because that is the operation for accessing a member of a structure pointer. Now, if your struct wasn't a pointer, then it's simple enough to just use the dot operator. And if you're familiar with Java, you use the dot operator for a lot of things in Java. This is like the C equivalent. We use it for structs. I like to think of structs as objects for C, but they're not objects, but they're the closest thing to objects in C. So there's the dot operator. Now, there are a couple of other things to keep in mind when using a struct. So I'm going to go to my useful resource, and I'm going to the struct section. All right. So it says here that structures can be used as function arguments, which means, like with a variable, you can pass structs to your function and use your struct in a function. Question? No? Okay. So you could also create pointers to your struct. And there are a couple of things you can also do with structs, and that's how you initialize and use them. So if we take a look at this example here, you see that for both my struct group and my person struct, we're able to use an initialization list to define it. That's great. You can use it it's very versatile to use the initialization list with structs. You could also explicitly state the values for your members. Let's see if I've done that. So using the dot operator like we see here, we could explicitly define what those values are, or we could use in a list. So you have both options when deciding how you want to put values into your struct. Is you could do it when you create the struct, or you could do it after you've created the struct by directly accessing the members. All right, so any questions on structs?
Union still, isn't that much of a difference between a union and a struct?
There isn't that much of a difference, but let's take a look, see what that difference might be. So if we look at the union, a union is a struct that, or it's a chunk of data of different types that store the same value. So to think of it like this, let's say we have a union called real numbers. Now, real numbers can either be a whole number or they could be a decimal number. They're still real numbers. So you can define a union as a real number, and inside you would put, for example, int x, float y, double z, correct? But when you put a value into your union, all those variables will have the same value, but in different representations, which lets you use the same value in different scenarios. So you can have an integer 0, but you could also have a double 0. You could also have a float 0. So you have that versatility of being able to have different variable types for the same value. So it lets you do very fancy things. A lot of things we don't need them to do, really. It's kind of nice, like for example, if you create a union with real numbers with different data types, then if you choose the wrong specifier, like if you chose the %d for your union, but you only have a float value and an integer value defined, it will know to use the integer value of your union. It will know to use the float value of your union. The values themselves are the same, but the data type is different. That helps you sort of decide how to use it. So right now we are at the 14-minute mark, so I want to try and sort of recap everything we've talked about and also answer any last-minute questions. So let's just quickly recap what we see here. So what can you tell me about variables?
They hold data of different types.
Variables hold data of different types. Excellent. Now, what types can variables hold? That's not a type, by the way.
In short, letters and numbers.
Yeah, letters, numbers, strings, a lot of things we're very familiar with. There's probably a variable that can store its value. We also have variables called pointers that store memory addresses, and we've seen how useful pointers are to a lot of the different things that we use them for in coding. We didn't really touch upon program flow during this session, but what do we know about program flow? How do we decide what to do next in our code?
Unless otherwise specified, it goes line by line.
Unless specified, your program is linear. The first line will be executed, followed by every subsequent line. But we have the option of skipping ahead, going back, looping, and that's all program flow. We have if-else selection, we have switch cases, which help us decide what to do next. And then we have while loops, for loops, do while loops that help us iterate through various things. So we also didn't touch upon arrays, but what is an array?
A list of cells that are all the same data type.
The list of cells are all the same data type. You could easily just visualize what the array is, just like a sequence of boxes, each with its own value. Special thing about arrays is that they have element numbers that start at 0. A lot of people get into trouble when they try to access an array but forget that the first element is 0 and the last element is the size of your array minus 1. So there is an issue called array out of bounds exception that commonly happens where you try to access an element of your array that isn't part of your array. So if our array was size 5, but you wanted to access cell 5 or element 5, you'll run into issue because element 5 doesn't exist. Element 4 exists, which is the last element of your array, but 5 is the size. You can't access the size portion of your array unless you make it bigger. So that's arrays. And another thing I want to note about arrays is that in order to use strings, we use character arrays. So a string is a character array that is special in what sense? What differentiates a string from a character array?
Null identifier.
Null identifier?
I thought null identifiers only in character arrays. Aren't strings just character arrays?
Strings are character arrays, but you have to be able to distinguish between simply a character array and what you want to be a string. There's a very special double quotes. Double quotes do let us know when defining a character array that it's a string. Now, why does double quotes work? Why does that let us know it's a string? There's a special character at the end of a string, and that is the end of string character, which is a \0. At the very last element of your character array is this value. Without this value, your character array isn't considered a string. It's just a character array. So an array you create to store a string has to be 1 bigger than the string you're storing, because you have to include this terminating character, this end of string character. Without this character, you can't say that you have a string in C. It will simply be a character array. So the addition of that symbol makes it a string. So you find a lot of times that when using and manipulating strings, that the array you store your string in is one bigger than the string. So if our string was hello, which is 5 characters long, the array that we store it in has to be 6 long to account for that end of string character. So that's something to keep in mind as well, is that the very last element of your string isn't a character, it's a null character. It's an end of string character. So keep that in mind when using strings, is that you have that extra element that doesn't contain a char that you need to use. So with functions, we talked about how you can define the prototype as a return type followed by the function name and your parameters list. And I mentioned that when you're using functions, you have to make sure that the initialization and the definition itself are toe-to-toe with each other. If you have 3 parameters in your prototype, then your definition also has to have 3 parameters. If your prototype has a void return type, then your definition also has to have a void return type. And that avoids a lot of issues down the road. Now, recursion, we saw with the factorial example, is simply a function that calls itself. And we noticed with the stack that we can run into issues if that went on forever. So with recursion, we have a base case that tells us when to stop. So we're going to keep calling our function until some base case is found, and then we're done. And that avoids a lot of stack overflow problems with your recursion. All right, and we saw structs, how they can be initialized, how they can be defined, and we saw that structs are used for data structures like linked lists and stacks and queues, and that you'll need to have a good understanding that a struct is simply just a packet of data, and you have access to those individual packets. And then we talked a little bit about file I/O and the differences that you might notice between sequential and random access. I like to think of it as sequential tends to be files that you can read, while random access files tend to be in binary and you're not really sure what's in there. And there are various functions for manipulating that file, opening it and closing it. And it's a really good strategy to conserve memory, in the sense that if you're finished with a file, then you should close it and remove it from your program if you're no longer using it. And we also have, we kind of talked about data structures, malloc and calloc, and that calloc sets default values, while malloc just reserves the space, and you kind of pray that the values in there aren't that bad, but you don't know when using malloc what those values might be. But with calloc, you have some idea. So for the last 6 minutes, I just want to briefly just look through this list of very common programming errors and how to avoid them. So the first one we see is improper comment characters. Now, a very easy thing to mess up when using a comment, for example, is we know that for a multi-line comment, we tend to use backslash, asterisk, asterisk, backslash. If you forget one of those asterisks or backslash, then you accidentally comment your entire program. Your entire program becomes a comment. So when you click compile, nothing happens because you forgot to close your comment. It happens quite a bit. I still do this every now and then. I'd forget to put an asterisk and wonder why my function isn't working. So it's good to keep that in mind. Undeclared variables and functions. So we talked about this. You can't use something that doesn't exist. So if you want to use a function, if you want to use a variable, you have to make sure you've created it first. It's very
common to see someone, for example, they would write out a function definition, but they wouldn't include the prototype. So your compiler won't know you have that function to use until you've defined it. Missing braces and indentations. It's very easy to have a logic error when you forget a brace, or even when you forget a semicolon, because that confuses the compiler. It doesn't know where to look, and it can throw an error at your face. So remembering to close your braces and remembering to end your lines with semicolons will help avoid a lot of that. I mean, it still happens. There's a reason these are very common, because they're not common because you don't know to do it. It's just a very easy thing to not do. You know, just when you're typing out quotes, for example, it's very easy to forget the ending quote, or you use the wrong quote by accident. Like how we were talking about characters and strings, characters use single quotes while strings use double quotes. So if you try to use the wrong quote, you will run into issues. Array bounds. As I said earlier, arrays start at 0 and they end at the size -1. So when looping through your array, you have to make sure that you don't go beyond the scope of your array. And that's a memory leak issue also, if you wanted to know, is that if you go past the scope of your array, you go into memory you shouldn't be accessing. Because an array is just a chunk of memory. So if you go past that chunk, you're in memory you shouldn't be accessing. Now scanf and printf using the wrong specifier leads to issues. So knowing what specifier to use in which scenario helps avoid a lot of these. Operator precedence. It's not really stressed that much, but when you're using math in C, there is PEMDAS. Your computer knows an order to do its operations. So if you put your operations in a illogical order, you might not get the result you're expecting, not because the compiler doesn't know how to do math, but it's really that you don't know what PEMDAS is. And the computer knows PEMDAS. So for example, it says 5 plus 7 minus 9 divided by 8. Because we know PEMDAS, this division will be the first operation to happen, followed by the addition, followed by the subtraction. An easy way to avoid any confusion with the order of operations is to simply use parentheses. Because parentheses have the highest order of precedence. So whatever you put in parentheses is what your program's gonna tackle first. And I just wanna talk about an infinite loop. So like with recursion, without a base case, we're gonna keep making those function calls and overload our stack. With a loop, without a condition that tells us to stop, we're gonna keep looping until the end of time, really. Until you run out of memory, until your program crashes. It's not a good thing to have an infinite loop. And then last one, not really, the biggest thing to worry about, but it happens. Don't divide by 0. It's not possible. Program doesn't know what to do. Mathematicians don't know what to do. Try to avoid dividing by 0. It happens. There's a lot of ways you can end up dividing by 0 by accident. But that is an error you would see if it does happen. So those are common errors. A trick to avoiding them is to just be cautious when you're writing your code. Be vigilant to avoid these errors. And that's today's review session. I hope I helped you guys out a lot. If you need more tutorials, I recommend watch a couple YouTube videos on whatever you didn't understand that much, but hey, wish you guys the best of luck on your exams.
Thank you.
If you guys have finished those surveys, I'll just collect them.
So the number on the box is what we're supposed to put in the inputs?
Sure.